This is page 23, and we're going to deal with a little break-even analysis. So we have two equations here, and we're looking to see, and just to give you some background on this, that one of these lines might look like so, and the other lines might look like so. So we're trying to see where these lines would intersect if we were to graph them, but we can find them out algebraically. So the strategy, I think, would be to put them in slope-intercept form. I'm going to bring this y over to this side and then write it over here. Y, it's now a positive y, equals 6x. And I'm going to bring this 4 over as a negative 4. So I've just written this equation, rewritten it in slope-intercept form. Now I'm going to do the same with this one here. Y equals a negative x, I just have to switch these two around, plus 10. So the technique for solving these, I believe, would be to equal, since y equals y, to have this equal this. Now we solve it, because this is a y and this is a y. Y equals y. So this becomes a 7x on this side. Transpose this becomes a 14. Divide both sides by 7, we get x equals 2. So our first member of the ordered pair where they're going to intersect is at 2. Now if x is 2, I can use, let's say, this equation here. X is 2. 10 minus 2, that would be y is 8. So the intersection of these two lines in a graph would be at 2, 8. All right, let's do this one, because this one's already set up as y equals y. So we can go 9x minus 2 equals 2x plus 5. Now we transpose the 2x to this side, and that becomes 7x. Transpose the negative 2 to this side, becomes a positive 2. 5 and 2 is 7. So x, and if I copy the example down correctly, that makes a lot of difference. Yeah, this is a 9 here. And I got a 2 out of that. So I'm going to transpose the negative 9 to this side, becomes a positive 9. So 5 and 9 is 14. There, that's better. We're going to divide both sides by 7 now, and we get x again is a 2. So we have one of the ordered pair members. So if x is 2, we can put it in this one. 2 times 2 is 4. 4 plus 5 is 9. My other ordered pair member is a 9. And by the way, if you were to put these into these equations, it makes both of them true. And again, the answers are on page 25. Now in number 3, after reading this over, and we'll give you time, we see this is something we've done before, where this is our cost function, and this is our revenue function, and they're looking for a break-even quantity. So we said this could be substituted with a y, and so is this one. So we then get 12x plus 1400 equals 100x. So we're going to subtract 12x from both sides and get 88x equals 1400. Divide both sides by 88 and we get x equals 15.90, and this part repeats. So they're wondering when they would break even, so I think we'd round that off to 16. They'd have to sell 16 of these units in order to break even. Actually, there'd be a little bit of a profit there. Now in example 4, again something very similar. X is the number of tickets that you want to sell. So you can cover the, I don't know if that's a new stadium there, but it's some kind of repairs to a stadium. It's not very much money. But I see the tickets cost $600 each, so I'm not sure what's going on there, but it's just mathematically giving you something to put into a formula. This will be y. This is y also. So we have 450x plus 15,900 equals 600x. We're going to subtract 450x from both sides, and this leaves us with 150x there equals this. Divide both sides by 150 and we get x equals 106. So it must be a rather small stadium, and again, we're not looking at that. We're just saying this would be the number of tickets sold to cover the cost of the building or whatever, the repairs or whatever, to break even. For example 5, we're going to give you some background. Here we have revenue in trillions of dollars from the sale of X units at a supermarket, and this is the revenue function right there. Now they're giving us a profit function, and the profit function is here, but where does profit function fit in? And the general formula for profit function is equal to the revenue function minus the cost function. So what we don't have is what is the cost function. And I changed our color here a little bit. Now we know the cost function is going to incur some cost to produce a product. This will be our number of products. And we know that when we subtracted the cost, that whatever was in this position, because of this negative sign here, became negative. So we look at our profit and say, in the cost function, this is going to be a positive. So we get a 0.9 there. Now, we know also then we had to subtract what the cost of producing each item was from our revenue. So there is our revenue function right from there, and I added a 0. So when we do our subtraction, we can do this a little better. So if we subtract now the 0.081 from this, we get 0.199x. And we know we had to change that sign to a positive. So our cost function then is 0.199x. So just reviewing where we've been, profit equals revenue minus cost. They're giving us the profit function. They gave us the revenue function. What they didn't give us is the cost function. So if we subtract this profit from the revenue, we then get the cost of making a particular item. And since we had to then subtract this fixed fee, that goes from negative to positive. So if you were to put this formula here and subtract it from this, you would then get this formula. But we want to know what the break-even point is. So this is a y, we said. No, not that one. This is the y here, and this is the y. So we're going to get 0.199x plus 0.9 equals our revenue here, 0.280x. Now we're going to subtract this from both sides, and we get 0.081x. Now to solve for x, we're going to divide both sides by 0.081. 0.081. Put that in your calculator, and I've worked this out already, and x equals 11.11. And there we are. And we rounded it off to the nearest hundredth. So this is approximation. So this one was a little bit challenging here, and I have to be careful about what I write sometimes. Okay, let's go on to the other page, and again rounding this off to the nearest hundredth. Now here they're saying when 5 items are supplied, what is the price? So we're going to analyze a little bit of what's going on here. Where is 5? Well, 5 is right there. And as we go up, we see the point right there over to this line. It will be $30. So hopefully something easy. And this is often, by the way, what supply and demand graphs look like. And in one of the courses I worked with, they actually helped derive formulas like this. And the background is that if you have strong demand and your supply, there is a point where you kind of seek what would be a reasonable price for something. And that would be an equilibrium point where the lines intersect. But here they're only asking, when 5 items are supplied, what would be the price? So 5 for the quantity, and then you go up here and then over to the left, and you get $30. Now for number 2, the equilibrium quantity is how many units? So again, you're looking for the point of intersection, And then here you're going down and seeing it's 144. So a couple of easy things here. In example 3, we see let 1 week's supply S and demand function for gasoline be given by this one for demand, which I've set up this way, and this one for price, which I've set up this way. So demand and supply. So we've sketched it into a little graph, and again we're suggesting that y equals y, and we solved this adding 1q. Now normally we don't put the 1 there. I put that there for emphasis. We get 3q equals this, so q, which is your equilibrium quantity, is 100. Now on our graph, if we take this 100 for q and put it in there for q, 100 here, 2 times 100 is 200. That is the equilibrium price. And the interval that demand exceeds supply, as you can see, is down in this area, which is 0 to 100. Okay, well, hopefully this is helpful. We finished our first 24 pages. I saw that a few of the answers were incorrect, but hopefully we are moving in the correct direction.